Okay, off we go. So here's what we're picking up from last time. So a quick reminder what the DF matrix is, right? So the DF matrix is part of our formula that we have here that we are using as what we're calling a linear approximation of a vector-valued multivariable function. And so this DF matrix does most of the heavy lifting in this construction. Reminder then that what the matrix is, well, here it is. What the matrix is this right here. Right? It's a matrix consisting of all the various different partial derivatives of the various different output coordinates, right, of the vector value function with respect to the various different input coordinates of this multivariable function. Okay, so now looking carefully at, let's pick a column here. Let's look at that first column of this DF matrix and notice, well, we've previously noted all the partials are with respect to x1, but furthermore notice what we're taking the partials of are literally all of the coordinates of f itself, all of the output coordinates of f. So the vector of x1 partials of the different coordinates of f is just the partial of the vector f with respect to x1. And so that's the first observation that I have here on the next page, is that the columns of your DF matrix are the various different partials of the vector-valued function itself. And that's just sort of an organizational observation, but it's nice to make note of that. Now let's go back over here and look now at the rows, and what can we say about the individual rows? So this row here, for example, well, yeah, it's always, everything in here is a partial of f1 with respect to something. And then you notice, in fact, this is the partials of f1 with respect to all of the input coordinates. This is something we've discussed before. This is the gradient of f1. So not only do the columns have a reasonable interpretation, but the rows have a reasonable interpretation as well. The rows of the DF matrix are the gradients of the individual coordinate functions of your vector-valued f. So just a couple of neat observations. And then one other thing. We call L the linear approximation, and it's a little bit of an abuse. Technically, L is not linear. Right? You all just took a course in linear algebra, right? And linear functions can't have a constant term. L does have a constant term, right? So technically, it's what's called an affine function. It's not actually linear. But the reason that we allow this kind of abuse of the terminology is that the thing that's doing most of the heavy lifting in the linear approximation, this DF matrix, well, that's it's a matrix, and so of course that's definitely linear. And so again, since this is doing most of the work in the linear approximation, it's a little abuse to call L linear. The reason we do is because DF is linear. Okay, moving along. Hope you all remember tangent lines. I'm going to spend a couple of minutes talking about tangent lines just to make sure everybody's on the right page. Again, a lot of single variable calculus classes, there's little abuses of terminology that they allow students to kind of develop some bad habits. So I want to make sure we clean that up. So as we've discussed before, here is our linear approximation function for a single variable function. That again, linear approximation is a function. It's not a line. Right? There is a related line, and that is the graph of the linear approximation. The graph of the linear approximation is a line, and it's what we call the tangent line. Now, because the function is best approximated, as well as is possible, mimicked by the linear approximation. In the same vein, the graph of f and the graph of the linear approximation track each other as well. Right? So that's why this graph of the linear approximation is, in fact, tangent to the graph of the original function, and thus we call it the tangent line. So that said, do please make the distinction. The tangent line is the graph of the linear approximation. It's not the same thing as the linear approximation. And again, you have to, the graphs are not the same as functions. It just matters. So heads up about that. Okay, so again, that's just cleaning up old news. Here, I'm going to take all those same ideas and just apply them to now a multivariable function. The only multivariable function that we can actually draw a graph of, and that is one that has two variables. Right? So looking at a function of two variables, a nice easy example of a graph of a function of two variables there. And keeping in mind this is a graph. So we can again talk about the linear approximation itself. Discussed this formula last time, right? The gradient is playing the role that the derivative was in the single variable case. So there's our linear approximation. Again, that's a function that is not a geometric object. That's an algebraic object, right? And analogously, we talk about the graph of that linear approximation as being the tangent plane. And again, the reasoning is it's really the same exact reasoning. If the linear approximation function is mimicking the f function, then the graph of the linear approximation should track the graph of the function it's mimicking. And so thus the term tangent plane. Okay, how we doing? Everybody happy? Yeah.
I just want to make sure, like the smaller rectangle is, you're saying like the tangent? But
Yeah, well, this is my attempt to draw a plane.
Okay.
So the graph of f itself is some surface, a curved surface. But this what I have in blue here is my attempt to draw a plane that's kind of tangent to that curved surface. Yeah, exactly. Okay. All right. So like I say, just a little bit of terminology, extending old ideas. And we move along now to a little bit of an awkward topic. We kind of swept something under the rug previously, and let me go back to where we did so. We started writing down formulas for linear approximations, right? But I put this qualifier up here. This is if the linear approximation exists. And we really kind of have to put that up there. We have to presume that it exists in order to be able to make sense of, for example, f prime, right? What if the function's not differentiable? Not every function's differentiable. In such a case, well, the linear approximation's not going to exist, right? So that we had to kind of put this in here, if it exists. So now we want to entertain, when does it actually exist? How can we know what we've written down as a linear approximation? How can we know that it actually does what we claim that it does, or maybe it's just a bunch of garbage nonsense that resulted from applying ideas that just don't make sense in the reality of the context of some specifically bad function? How do we deal with that? So here's an example of kind of what I'm talking about and what can go wrong. Let's entertain this function right here. Perfectly reasonable function. Doesn't have a formula as we're accustomed to, right? But this is a perfectly reasonable, what do we call it, rule of assignment. You give me an element of the domain, you give me an x and a y. I can look and see if either of the coordinates is 0. Right? Otherwise, if neither of the coordinates is 0, and depending on which of those happens, the value of the function is either 1 or 0. So not hard to persuade yourself, I believe, that above the axes, the value of the function is 1. Whereas off of the axes, the value of the function is 0. Yeah, it's hard to fill all that in. There we go. Like that. All right, so perfectly reasonable function. Let's take our formula for linear approximations, a couple pages back. Let's write it down. There's not that much to it. Let's see here. I'm going to clean up the thing here. Here's what we need to form a linear approximation. I need to know the value of the function at my the point where I'm doing the linear approximation, by the way, is at the origin. So I need to know the value of the function there. I need to know what is the gradient there, namely what are the partial derivatives there at that point. And I can just write them down, and then there comes the linear approximation. So let's do it. What is the value of the function at 0? Well, that's going to be one of these. And so the value of the function at the origin is 1. And then let's see, what can I say about the partials? Well, okay, let's see here, color choices. Here we go. If I'm at the origin, and if I start moving in the x direction, now very importantly, I'm at the origin. And then from the origin, I start moving exactly and only in the x direction. Well, then the value of the function is just straight up 1, and that is not changing, and so that partial with respect to x is 0. And then likewise, what if I'm at the origin moving in the y direction? Well, then the value of the function is still just always 1, and that partial derivative, therefore, also 0. And so all this together, just looking at the value of the function and the value of the partials, and all together, our linear approximation based on those is just 1 itself. So I'm going to try to represent that by doing some kind of like that. There's your linear approximation. It's just the value is just flat 1. The graph then of the linear approximation is z equals 1. Everybody with me? Okay, now let's ask the question, is this okay? Is this a good... would it be fair to call this a tangent plane? Is this doing a good job of approximating the function here? I say it's not. I say this is abysmal. I say this is a crash and burn failure. Because look at what happens if I entertain the fair, reasonable question of approaching the origin by way of a path coming through the first quadrant, like that. Right? So I start over here with positive values of x and y, and then I just make my way, perhaps curving, whatever, toward the origin, 0, 0. Well, the value of the linear approximation is 1, but what's the value of the function as I move along that curve? Well, as I move along this curve, as I have it drawn here, notice x and y are never 0, which means, I wanted to be in highlighter mode here, which means that the value of the function on this curve is just 0. So the value of my linear approximation is 1. The value of the function itself is 0. And I don't think that's a good approximation, right? As I get closer and closer and closer and closer and closer to the origin, my estimates keep being just wildly wrong. This is not a good linear approximation. Okay, now let's try to write down a reasonable first attempt at exactly what is it that this hopeful, candidate linear approximation, how did it fail? And the argument I would make here is that it failed because the value of the function minus the value of our our candidate would-be hopeful linear approximation. In other words, this difference, what you would reasonably call the error, these errors stay big all the way toward the origin. These errors don't approach zero. And I think it would be a pretty reasonable, again, sort of first instinct to think, oh, error is the bad. Error is what we want to not be there. Maybe we should just require that the error approach zero, right? If the error approaches zero, then what makes us unhappy goes away, and isn't that good, right? So reasonable first thought. It turns out that's not good enough. Now let me try to persuade you that this idea that error can just go to zero, let me try to persuade you this is not good enough. And I'm going to do so with another example. Let's entertain this example right here. Here's a function. This is a single variable example, you'll notice. Perfectly simple function, no problem. Suppose this formula right here we're hoping to pass muster as being a good linear approximation of this function f. And of course I can draw a graph of the linear approximation right there, and we have our graph of our function f. Now at a quick glance, do you think this green curve is would it be fair to call this a tangent line to the purple curve? No, not even close, right? And yet, look at the error. The error here, the value of the function minus the value of the linear approximation, the error keeps getting smaller and smaller. The error indeed approaches zero. So let's ask the question again for rhetorical purposes. Is it sufficient simply to require that the error approaches zero? And I think no, that's really not sufficient. If we simply required the error to go to zero, I would have to accept that green linear approximation as being a good linear approximation for this function, which it obviously isn't. So not good enough. Everybody with me? Okay, so here's the fix. We're going to look at something different, something not the same as error, something called relative error. And let me get into the right mode here. Relative error. So relative error is error, namely how far off are your output values, just like we saw on the previous page, divided by how far away are your input values. Keep in mind, we're doing our linear approximation at the point A. We're evaluating our linear approximation at the point X. And so we're this far away in the inputs, resulting in the values of the function being this far away in the outputs. Relative error would say, let's look at the proportion. All right, now with this in mind, let's think about our same example from the previous page. And let's see here. We had this function graphed like so. This candidate linear approximation drawn like so. Our errors are indeed approaching zero. The error is indeed approaching zero, but that's not the test that we're applying here. Here, we're interested in looking at the relative error. The relative error says divide by. Let's see here. Let me clean up the. Oh, okay. Give me a second here. Delete that. Here we go. So we're going to take our errors, which are these red distances. We're going to divide by our. How far away are we in the domain? That's those orange distances. And red divided by orange. You can see it geometrically here, or you can look at the algebra over there. As x approaches a, our error is getting smaller, but our input difference is also getting smaller. And this proportion, the relative error is approaching 2, which is not 0. So I'm going to call this good news. What we have now is a reasonable way to reject this obviously wrong linear approximation, right? The idea that 3x would be a linear approximation of 5x is silly, right? Requiring that the error vanish doesn't eliminate it, but requiring that the relative error vanish does eliminate it. So this is going to be our big test here. This is where our definition of a good linear approximation is going to come from. This is ultimately going to be our definition of differentiability. Is forget about error itself. I need the relative error to approach 0, and the convenient term for that is vanish. So vanishing relative error is what we want. Okay. Now, there is a lot more to say about this than I have said or that I have time to say. This is not the class for all that other stuff that I wish I had a week to talk about all this stuff. There's a tremendous amount of ideas that I'm glossing over superficially. The reason I'm covering this at all is because I want you to have a sense for kind of what the problems are, roughly speaking, and how we avoid the problems. And so is what it is, yeah.
Why are you taking the limit as x approaches 0?
Well, we're taking the limit as x approaches a,
Okay.
right? So as we approach the point where we're doing our linear approximation.
Okay.
Yeah.
That makes sense.
Yeah. So a just happened to be 0 here. Right. Okay. So here's the resulting definition, and we need for this expression here to approach 0 as x approaches a. What a weird expression. Where does that come from? Certainly the first time I saw this expression, I was a little kind of overwhelmed. Like, wait a minute, what do you mean? Where did that come from? There didn't seem to be much context. Why are there 3 terms? That seems strange. But let me just point out, all this is relative error. Relative error, keeping in mind, relative error is this thing I have circled right here. Don't forget that error is actual value minus estimated value. And don't forget that the estimated value, namely our linear approximation, is just this thing right here with, of course, some parentheses. I've got a minus sign here, but if I put a parentheses around the whole thing, then this would just straighten it. So morally, those 2 terms come from the linear approximation itself. So that's all that expression is. It's just relative error, fully expanded. Okay. All righty. Now, I'm going to make an observation about this expression right here, and that is it's hard to work with. It's a magnitude divided by a magnitude, which means there's going to be square roots involved, and that's really hard to deal with. Also, when I say approaches 0 as x approaches a, notice this is a vector x approaching a vector a, and in fact, you may recall we skipped the section on multivariable limits. And that's a lot of stuff. There's a lot of ideas in there as well. They're also sophisticated and complicated and hard to deal with. Because again, this is not Math219, and it's just not what we're here for. So I'm going to say this is a hard to work with expression. And if we needed then to show that a function is differentiable, this is the definition of differentiability. If I needed to show that a function is differentiable, in other words, that the formula that we think gives a linear approximation actually does, we'd have a bunch of ugliness to deal with. So we're going to be highly interested in finding other ways to conclude that a function is differentiable, because we really need this. We need to be able to talk about functions being differentiable so that we can write down this formula. I mean, again, this idea of being able to do linear approximations is really important. We can't do it. This is garbage nonsense unless you know the function's differentiable. So that's a problem. And good news, we're going to be fixing that problem on the very next page. But before we get to that, just a little bit of terminology. This big thing right here, previously, seconds ago, we viewed this as being the actual value of the function minus the linear approximation to the function. That's a fine way to think about it. Actual value minus estimated value. Sure. Here's a different way to think about it. Just as good. Actual change in the value of the function minus estimated change in the value of the function. So you can think of this as a difference of values, or you can think of this as a difference of changes. Right? And so just a little bit of terminology. We're going to be using these ideas a lot going forward. If you want to talk about the actual value, the actual amount that a function has changed between a point A and a point X, we call that the increment. And if you want to talk about the linear estimate, that's called the differential, written as df. So in some sense, differentiability is about a relationship between the increment and the differential. Okay. All right. Okay. So moving along. Here's our workaround. It's going to be really important to be able to conclude that a function's differentiable. Again, we need to be able to talk about linear approximations. We're going to need to be able to do things with the derivative matrix. We need it to not be garbage, as we saw in a couple of previous examples. So how can we conclude differentiability? It turns out that there's a really easy way to do it. This is totally awesome. It's this thing called continuous differentiability, which sounds harder. And in fact, continuous differentiability is a stricter condition. Fewer functions are continuously differentiable. It's a harder condition to satisfy. But it's a much, much, much easier condition to check. Because all you got to do is check that the partial derivatives exist. That's easy. You take the partial derivatives. There's nothing to it. It's world's easiest differentiation, right? So just check that the partial derivatives exist, and then check that the partial derivatives are continuous. And how do we know if a function's continuous? Well, the full story is a long, complicated story, but we know from long ago certain nice results, like all polynomials. They're all continuous. Every one. Everywhere, no problem. Every polynomial is continuous. You don't have to get all epsilon and delta with it, right? It's just known fact. Likewise, exponentials, logs, trig functions, practically every function you've ever seen before is continuous where it's defined. And a lot of people raise their eyebrows when I say that, and they're like, wait a minute, no. Tangent is not tangent has some nasty discontinuities, and it does, where it is not defined. But if you think about it, everywhere tangent is defined, it is also continuous. So it's easy to take partials, it's easy to eyeball glance and make sure that they exist, and it's easy to eyeball glance and confirm that they're continuous. So that's this idea of continuous differentiability. And now, again, that wasn't our question. Our question is about differentiability. We're looking for a way to conclude. Looking for a way to conclude that a function is differentiable. What does continuously differentiable have to do with that? Well, continuously differentiable, being a strictly stronger condition, gives us differentiability. So this is the big little mathematical life hack for how to conclude differentiability. Just check that it's continuously differentiable. It's easy to do. Take some partials. Observe that they exist and are continuous. Declare victory. That make sense? Pretty awesome. And we don't have to deal with any of the ugliness on the previous page with multivariable limits and vanishing relative error and magnitudes and square roots. And, it's horrendous. Don't need any of that. This will do the problem for us, yeah.
So if it's only implied one way, what if
Yes.
the function's differentiable but not continuous?
Correct. There are some such functions, and if this were Math 222, then we'd be worried about that.
Okay.
And this being Math 219, that's just not going to come up in this class. Yeah. Which makes me a little sad. It is beautiful math, but it's not our problem.
Okay.
Yeah. Okay. All right. So here's a quick example. Suppose you are interested in this function right here, and in particular, maybe you want to do some linear approximations, or maybe you want to talk about the gradient and draw certain conclusions of various sorts, and you need for this function to be differentiable before you can do any of that. How do you know if this function is differentiable? Well, here's what we do. Let's see. Let me go back up where we can see the definition. I compute the partials. Now, that's easy. I don't even have to write them down. It's obvious. This being a polynomial, the partials are all polynomials too. Polynomials we know are continuous. Again, old news, right? We know that from long ago. Polynomials never fail to exist. Polynomials are always continuous. That means that this function f is continuously differentiable. Everybody on board so far? And because it is continuously differentiable, it also follows, as we were hoping, it follows that it's differentiable. Everybody good? All right, now I do want to point out, this is just a quick comment. This is not really a math pseudo math, but anyway, this is important for the course. On an exam, if you encounter a question like this, or likewise on a homework, or anywhere in the context of this course, if you find a question like this, keep in mind. I know you've heard me say this a million times, but this is not a course about answers; it's a course about reasoning, right? So this argument that I've written here is very terse, right? But all of the critical elements are here. Everything's represented. Now, a lot of students will do the following. A lot of students will maybe just kind of not write this part down. And let's entertain the question. Looking at what remains after that's been scratched off, is this a complete argument? Well, it says here we've computed the partials. The partials are polynomials. Yeah. Okay, and so just going straight to this function being continuously differentiable? Wait a minute, the definition of continuously differentiable doesn't say polynomial anywhere. How does these being polynomials make it continuously differentiable? Now, it is true that if the partials are polynomials, then the function's continuously differentiable. That's a true statement, but it's not clear. Right? That's not how the reasoning works. The reasoning required, the only thing that makes that work is the fact that those polynomials, those partials which are polynomials, are continuous. So if you leave this off, if you leave off the continuity, then you've left off a really critical part of the argument. So make sure to keep that in mind, right? So keep in mind, this always weirds students out, but a math class is really a lot like a history class. You have to make your case, you have to explain your reasoning, and you can't assume that your reader knew what you meant when you glossed over some key aspects of the argument. So be explicit, hit all of the critical elements of your argument. Okay. All righty. Another little quickie. And again, I'm not going to prove these results. These are just things I want you to have seen and that you know how to use them if you need them. But every differentiable function is continuous. You can just take my word for that. Yeah, this is not very useful as written. This suggests that I would go to all of this horrendous trouble of checking that a function is differentiable just to conclude that it's continuous. And checking whether it's continuous is much easier. So that's a weird statement as written. But now notice down here, this second statement is an equivalent statement, in fact. This is called the contrapositive, right? So if a statement is P implies Q, the contrapositive says not Q implies not P. And you can kind of think through that morally those say exactly the same thing, right? Okay. This one actually is pretty useful because sometimes it's really easy to tell that a function is not continuous. So look at this thing down here, for example. This function here is definitely not continuous. And the contrapositive then immediately tells me an answer to the much harder question, namely, is the function differentiable? Answer, no, definitely not. Can't be differentiable because the function's not even continuous. So, neat little, clever little trick, little mathematical life hack. Something to be on the lookout for. Sometimes handy. Okay. How we doing? All right, moving along. So let's talk about our linear approximation formula now. And here it is. And I can finally write that down with a clean conscience and not have to worry about whether I'm applying a formula that doesn't make sense for the function in question, because you see I'm applying this only to a differentiable function f. And after all of that effort that we went to several pages back, we know exactly what it means for a function to be differentiable. And when you have a differentiable function, this is truly and appropriately a good linear approximation. All right, everybody okay with that starting first step there? So, now just a real quick tweak. A linear approximation has to agree with the function at the point where you're creating it. That value I can subtract over to the other side of the equation. No big deal there. And now look at where we've gotten to then. This formula here tells me that my derivative matrix is what you multiply by the input change. Right, after all, x minus a is how much did my input to the function change as I moved from my starting point a to my point of interest now x. So this is input change. This is called the input differential, sometimes written dx. And when you multiply by the df matrix, what you get is, let's see here. You don't get the increment. You don't get the actual change in the value of the function f, but you do get how much the linear approximation changes. Namely, you get our linear estimate of how much the function f changes. Namely, you get what we call the output differential, df. So, how about that? This matrix, the df matrix, which I'll remind you, we first wrote down this df matrix as a notational convenience. I just didn't want to have to write down all those terms with all the dots, right? It's very clunky otherwise. This is a nice little convenient shorthand, right? But now we have a much deeper interpretation of this df matrix. That df matrix is what you do to input changes to learn about output changes. It's the relationship between input changes and output changes. And you may recall the very, very first thing that we said about derivatives at the very start of section 2.3, I guess it is that's what derivatives are. Derivatives are relationships between input changes and output changes. And df does it. So because of this equation right here, this thing df, colors, df we call the derivative. Or if you want to be more explicit, more blunt, it's the derivative matrix, just as a reminder to your listener that, of course, it's a matrix. Or if you'd prefer and ask, suit yourself, doesn't matter, you can call it the derivative transformation because it's a linear transformation. Take your pick. Any of these are fine. So now I've made the observation before that there's many different kinds of derivatives in this class, and that they play different roles in different contexts, and we call them all by the name derivative, but that partial derivatives are not my favorite. They're certainly not what I want you to think about fundamentally. When you leave this class, I don't want you to think about partial derivatives as being most fundamentally what a derivative is. No, absolutely not. It's this matrix, the DF matrix. This is the thing that turns input changes into output changes. No strings attached, no narrow applications only. Partial derivatives only make sense if most of your input variables are constant. That's weird. How often does that happen? That's unnatural, right? So partial derivatives are very narrow in their application. Gradient vector, right? Remember we talked about how the gradient vector can be viewed as a derivative? Yeah, but it only makes sense for real valued functions. You can't really make sense out of it for vector valued functions. No strings here. Multivariable, vector valued. I don't care how many of the input variables are changing. DF turns input changes to output changes. Okay, so again, when you leave this course, when someone says the derivative, I hope this is the first thing that pops into your head. Okay. All right, now just to give you a picture of what's going on here. So let's start with, let's suppose I have a function f, and there's a point A, and then here's the point f of A, and a function takes an input point and produces an output point. That's what a function does. Point in, point out. The derivative takes input changes and turns them into output changes. The derivative takes, in other words, this input vector and produces this output vector. Right, so again, a function takes a point to a point. A derivative takes a change to a change. Everybody all right? Linear estimates, of course. Okay. All right. Now, here's a tweak of this idea. Let's suppose that everything involved is a function of time. So, for example, maybe x and y are like longitude and latitude, right? And then let's suppose that my function is keeping track of a couple of aspects of weather, like, temperature and barometric pressure, whatever. I don't know, something like that. Something that I'm experiencing as I move through the domain. Well, if I'm at this point A, I would be moving with some velocity. I could very reasonably ask, as I move with a given velocity, my position is changing. That means temperature is going to be changing and pressure is going to be changing. That means that the value of the function is going to be changing. Given my input velocity, what is the corresponding output velocity? And notice all you have to do to turn, the answer that we know how to relate differentials. Just divide both sides by dt. And notice that then turns my input velocity into my output velocity. And notice it is the same derivative matrix that does this. Still, the derivative matrix turns input velocity into output velocity. So this, I think, is another really, really nice interpretation of the derivative matrix. For whatever it's worth, I find this more intuitively satisfying than the one on the previous page because it's instantaneous, because there's no approximation involved, right? This is not, I'm not saying that this is our estimate of the output velocity. This is our output velocity. Again, assuming the function's differentiable. So, pretty satisfying. Okay. All right. Let's see here. The last observation to be made down here is this is really a quick one. And this is, I know this looks like a lot of algebra. There's really not that much going on here. All I'm doing is doing the same sort of first step that I did a couple of pages back. Rewriting the linear approximation by moving some things around. But this, for the real valued case, remember it's the gradient that we used. And so it's not matrix multiplication, it's a vector dot product. So how do we make the distinction, and do I really have to worry about this? And the short version is I don't really have to worry about it very much because keep in mind when you have a matrix, let's see, let me write this down. If you have a matrix that has a single row and you multiply it by a vector, right? So here I have matrix times vector. Okay, well, if I were to take this, let me just give myself some more room. If I were to rewrite the matrix as a vector and then dot, okay, let me make a different color choice there. Then dot with the same vector. Notice it's the exact same arithmetic. Right, the matrix vector product, that times that plus that times that. The dot product, that times that plus that times that. It's the exact same thing, right? So if you have a real valued function, sure, I suppose you could think of the gradient. I want it to be in highlighter mode. You could think of the gradient, dot product with the gradient as what you're doing, but honestly, feel free to just think of that as a matrix of a single row. Same deal. So, anyway, I just needed to make that observation. It's not really technically all that different. How we doing? All right. That same picture. So again, dot product with the gradient for the real valued case. Right? Now, of course, the gradient only makes sense if you have a real valued function. You can't talk about the gradient of a vector valued function. It's just not a thing. Right? But in the real valued case, dot product with the gradient is morally equivalent to multiplying by the derivative matrix. Okay, and let's see here. Looking at the clock. Well, so we got a minute and a half. That clock's fast. Okay, I got to remember that. Okay, so let me just say a couple of real quick things. This is a pretty straightforward observation here. When you take a derivative of a multivariable vector-valued function, the derivative is a matrix. A matrix is a linear transformation. Linear, right? Cool. Old news. Matrices are linear. There is another kind of linearity involved here. That is, instead of thinking of df itself, right, df being the result of differentiation, I can instead think about the act of differentiation. D by itself, just d'ing a function. You give me a function, namely a differentiable function, and the product, the result of applying d to that differentiable function is the derivative matrix. Again, we've already observed the result of differentiation is, of course, linear. But I'm saying, in addition, the act of differentiation is also linear. So if you were to take a linear combination of functions, the derivative matrices of the functions and the derivative matrix of the combination have that same linear relationship. So that's represented by this equation right here. And just a quick example of mostly arithmetic. Here's a couple of functions. All right, here's their derivative matrices, easily checked. By the way, also easily check that these functions are differentiable. Good little exercise. Make sure that you're comfortable with the idea of how would you confirm that these are in fact differentiable. Something to think about. Well, if you take this combination of those functions and look at its derivative matrix, then the combined derivative matrix and the original derivative matrices, these relate by way of the same coefficients 5 and 6 as produced this combined function h. So again, linearity of derivatives. Okay, and I'm out of time at this point, so we'll draw the line right here. We'll pick up here on Monday. Y'all have a great weekend. See you later. Don't forget to come talk to me if you came in after concerning attendance.